Okay, welcome everybody. This is the Motivic Geometry Seminar, and today's speaker is Steve McKean. Please, Steve.
Great, thank you, and thanks to Paul Arna for the invitation to speak. I'm really excited about this. It's fun to get to speak about Motivic homotopy theory and Motivic geometry, and I'm excited to do it with a bunch of colleagues, so hopefully we have a fun time today. So I'm going to be talking about basically a result that allows you to compute the A1-degree with a fair amount of generality and in a nice computational way. So that's kind of the general theme of the talk today, is the unreasonable effectiveness of commutative algebra and Motivic homotopy theory. And the new results that I'll be talking about are joint with Thomas Brazelton and Sabrina Pauli, and this is forthcoming work. So we're currently writing up some of these ideas, and hopefully we'll have that written up soon. So kind of the general outline of what I want to talk about today is I want to start with a brief recollection on Morel's A1-degree. This was kind of an early point in Motivic homotopy theory, where we started to see that there should be deep connections between interesting topological invariants that you want to work with and commutative algebra. Okay, and then the second result that I'll briefly recall is Kazanov's formula for the global degree of an endomorphism of P1. So this is maybe the first step towards actually making the A1-degree computable. It's a nice topological invariant, but if you want to actually work with it, then you want to have formulas you can write down and either tell a computer or a mathematician like me to compute. So that'll be kind of the second thing we talk about. And then the third thing we'll talk about is the work of Jesse Kass and Kass and Wickelgren on computing the local degree. So Kazanov's result is limited by the dimension in which you can work. You're just working in dimension 1. And if you want to work more generally, then Kass and Wickelgren give a method for doing that using local degrees. You break your global degree down into local degrees, and then you compute those local degrees using a formula that they write down, again, in terms of commutative algebra. But again, there are some restrictions on what you can do there. You have to worry about the residue field of a point at which you're working. If it's not a separable extension, then maybe you run into issues with your transfers, and there's kind of some details there to worry about. And another difficulty is if you want to compute the global degree, you have to compute all this local information. We'd like to kind of bypass that and have a way of computing the global degree in one fell swoop. So that is where Thomas, Sabrina, and I come in. We have kind of worked out a formula for how to compute both the global A1 degree and the local A1 degree using a fairly simple formula. So that is kind of where we're going to start. Okay, so let me begin with Morel. And we'll just recall what his A1 degree is. So the A1 Brouwer degree, you might say. Okay. So for endomorphisms of P1 over a field, this looks like the Grothendieck-Witt group of bilinear forms, plus a little bit extra. You also have some information coming from what's essentially going to be the determinant of your bilinear form, or the discriminant. We'll talk about that a little later with Kazanov's work. And then for n at least 2, you look at these endomorphisms of the sphere. And it's just the bilinear forms. It's just the Grothendieck-Witt group. Okay. And the general way that Morel proves this for n at least 2 is working with basically with sheaves and trying to make sense of what sort of homotopy sheaves you get. So there's a stable result that if you look at maps from S naught to a smash product of GMs, of these just multiplicative GMs, working with P1 spectra, you can compute this in terms of Milnor-Witt K groups. So this is just the nth Milnor-Witt K group. Or you could work unstably and have a similar result. Okay, so this is just showing us that the kind of the first computation on the A1 degree, at least to me, there's not a whole lot of commutative algebra showing up. I mean, these Milnor-Witt K groups have a nice presentation that's very algebraic, but at least to me, when I look at this, I don't think that computing residues in commutative algebra is really going to show up anywhere. Okay, but in both cases, you just get that maps of the sphere, of the n sphere. This is just the 0th Milnor-Witt group, which is Grothendieck-Witt. Okay, so this is kind of where our story begins. And I'll make the remark that at least when Morel first computed this, he computed these as isomorphisms of groups, and you could also compute them as isomorphisms of sheaves of abelian groups. But I think a question that I want to ask towards the end is, this should just be an isomorphism of rings as well. And I think that you can see that using maybe a more sophisticated approach to computing this degree. Our result will give an alternate approach to computing this degree as a ring isomorphism rather than as just a group isomorphism. But we can maybe talk about that a little later.
And the base field is general. There's no assumption on the base field.
Yeah, so in Morel, he assumes a perfect base field, but I think that it's in a paper of Oiwa that you don't need that perfect assumption, that you can kind of work around that. Yeah, but at least when Morel first did this, it was a perfect base field. Okay. But at least for what we're going to do, perfect doesn't show up anywhere. It really works in general. Right. So now let's do, we've written down a map, something that we think is interesting. It relates to the degree that you would first learn about in like an algebraic topology course or a differential topology course. And we've seen that that can be used to prove interesting theorems. So what if we want to actually compute this degree? And that's where Kazanov shows up. Okay, so Kazanov says, let's just look at degrees of endomorphisms of P1. And so I'm going to take a rational function in here. And I'm going to compute its degree using the Bézoutian. This is the first time we'll talk about Bézoutians, and this is the univariate case of a Bézoutian. So the Bézoutian of f over g it's just a bivariate polynomial given by you evaluate f at x, g at y, and then minus f at y, g at x, and divide by x minus y. So in this situation, we're presenting f and g as univariate polynomials. That's how we're writing down this rational map. So this makes sense. This is really just a univariate polynomial, and I'm just swapping out the variables either as x's or y's. Okay. And then Kazanov's theorem is that, okay, so you write this Bézoutian as a sum over I and j. We have coefficients in our field k, and then we just have respective powers of x and y. And then you can write down a matrix over k whose entries are just these coefficients. And Kazanov's theorem is that this matrix computes the A1 degree for you. Now there's two pieces of the A1 degree that we have to talk about. The bilinear form represented by this matrix over the basis 1, x squared, and so on. So with respect to the basis, one x squared, and so on, up to whatever power. This matrix is the gram matrix of the bilinear form in the GW component of this degree. So the degree of f over g is isomorphic to this Bij. And this is just in the Grothendieck-Witt part. And then you can also take the determinant of this matrix. And this will give you the K star factor of your degree. So this is a very explicit method for computing the degree using a Bézoutian. So I can do an example really quick because, at least for me, I need examples for anything to make sense. Let's take just a general polynomial as my f, and I'm going to compute the global degree of f over 1. So I'm not going to have g show up anywhere. Okay. The Bézoutian of f over 1, well, I can kind of shortcut, and I can write this as a sum of my scalars, but then the f of x minus f of y part is giving me these x to the I minus y to the i's, and then I divide out by x minus y. And so this generally looks like, well, I have x to the I minus 1 plus x to the I minus 1 minus 2 y plus, and so on. And we lose the constant part of this morphism. Okay, and so then if you wanted to write down this matrix to understand the global degree as a bilinear form, well, I'm just going to write down 1 x squared, and so on. And then down this side, I'm going to use y's just to help me distinguish. And then I can just fill in this matrix. My constant term is coming from the A1. And then I have A2, A3, 2, 3, 3, all the way up to AN, and everything else is 0. So now the trick just becomes, how do you diagonalize this bilinear form? But I'll leave that computational piece for a computer to do for me, or someone who knows how to use computers to do for me, because computers can be tricky. Okay, so the general idea behind the proof of Kazanov's theorem, there are two proofs. I'll first mention Kazanov's. So essentially, he works with, rather than working with A1 homotopy classes of maps, he starts by working with naive A1 homotopy classes of maps. So work with naive A1 homotopy classes. And he puts a monoid structure on these endomorphisms of P1 with respect to these naive homotopy classes. Okay. And then the next step is to show that you get a universal way of mapping from naive A1 homotopy classes to A1 homotopy classes, genuine A1 homotopy classes. And it turns out that this map is a group completion or a groupification. So, and naive maps to A1 maps is a group completion. And obviously there's more work there, but that's the general story behind what's going on. So that's one proof. Jesse Kass and Kirsten Wickelgren gave another proof of this using a more classical result. There's a result of Hurwitz that allows you to compute the topological degree, the real topological degree of a map, using some particular matrices. And so Jesse and Kirsten modified this proof to reprove Kazanov's theorem. So they modify a classical proof of Hurwitz. Okay, so two different ways to prove this, and it's at least suggesting that there really is maybe even a deeper connection to commutative algebra than we first expected, because you can take a classical proof of Hurwitz and modify it to say something about A1 homotopy theory. So at least to me, that suggests that there really is something hiding in the background here. A remark about this, so something that I had wanted to do was take Kazanov's result and just directly generalize it to higher n. And at least to me, there's not an obvious way to do this using either of these proofs. So Kazanov's monoid structure really relies on the fact that you're just dealing with one rational map. So Kazanov's structure really uses n equals 1. And in Jesse and Kirsten's proof, there are these matrices called Newton matrices that show up, and it's not clear to me how one would generalize those to higher n as well. So there are particular matrices that I wouldn't know how to generalize if I wanted to boost this theorem to hold for higher dimensions. So okay, but at least we have a start. We can compute some things. Okay, so the next step is, what if we want to compute the A1 degree of something in dimension 2 or above? What do we do? Okay, so next, how do we compute this global degree when we're in a more general situation? So and an insight of Kass and Wickelgren was, well, thank you, Kirsten. So yeah, so Kirsten's saying that her and Jesse's proof doesn't give this monoid structure that Kazanov gives. So Kazanov does give that explicit structure, but even just for computing the degree itself without talking about the structure, it's not clear to me how to generalize either proof to n equals 2, for example. So back to computing the global degree more generally, in an algebraic topology course, if you want to compute the degree of a map, you can compute it locally. You can look at the map at regular point, or like compute a regular value decomposition of your map, and then just compute these local degrees. And this is a classic thing that you would do in a first course in algebraic topology in graduate school or something. And so the idea was to take that same approach. You want to compute the global degree by expressing it as a sum of local degrees. Okay, so you take a k-rational point in the target and the codomain, pull it back, and look at local degrees over that fiber. And so then if you're able to decompose your global degree in this way, you can reduce a global reduction to several local, global computation to several local computations. So then you want to compute the local degree. Now we have to say what this local degree is. We have to actually define this. And this is just going to be a global degree of a particular composite that gives us a way of isolating one of the roots of f. So what I'm going to do is I'm going to take a small neighborhood of a point P and a small neighborhood of its image and study the map F in a situation. But for us, degrees should be maps of spheres. So on this side, we have a nice result that we've assumed Q to be K rational. I didn't write it down, but we're assuming that this is K rational. And so we can use a purity isomorphism to write this as a sphere. Okay. On the other side, we could use excision, but we don't quite get a sphere yet. And so we have to deal with this somehow. We want to be writing down an endomorphism of Pn over Pn minus 1. And so the solution is you start with the collapse map. So you basically collapse this Pn minus a point down to a Pn minus 1. Okay. And then this total composite, if I call it F, then the local degree of little f is just the global degree of this composite. Okay, so this at least gives us a framework in which we can say what a local degree is. And then the great insight and result of Kirsten and Jesse's paper is there's actually a way to compute this algebraically. You don't have to live in this topological world. You can write this down algebraically and actually get a bilinear form out of it. So I'll recall that now. Are there any questions at this point? Okay.
So whether two sets are different, for me, U over U minus P and V minus over V minus Q are of the same form.
Yeah, so these the way that I would think about this, like very, very roughly, is these are like affine neighborhoods of Q and an affine neighborhood of P.
Yeah.
But we're not assuming that P is K rational. So okay. Q is K rational. If P is K rational as well, then you don't even have to worry about this collapse map. But if P is not K rational, then you don't have this nice purity isomorphism, at least the way you would want it.
Okay, yes, right, thanks.
Yeah, I feel like my life would be so much easier if I could always use purity when I wanted it to, but it's these rationality questions are sometimes frustrating. Great. Other questions? Okay, so let's actually compute this degree. So the general setup, I'm going to, I mentioned that these neighborhoods, we can basically think of as affine neighborhoods. And so we're going to restrict ourselves to endomorphisms of affine space. And we're going to assume that we have an isolated root. The point of this is we're going to construct a local complete intersection, and we want this to be finite dimensional as a vector space over the base field. So if you didn't have a complete intersection, you would have something that was not a finite dimensional vector space, and it messes with some of the commutative algebra that shows up. So P, since it's an isolated point, an isolated zero, is a closed point, and it corresponds to some maximal ideal of the polynomial ring. Okay, so we have some max ideal in the polynomial ring. And I'm going to define a local algebra, which is just the polynomial ring localized at my point, and then quotient by the polynomials that generate my morphism. So essentially, the way that I think about this is I'm zooming in at just one point, and so there's only one point at which this morphism can vanish in this local algebra. And then we're just studying the properties of that morphism when we're just looking at this one point. So that's why this local algebra gives us a nice commutative algebraic picture of this like local neighborhood thing that we were doing topologically. Okay. So the big guns that show up to let us compute things now are Shear and Storch. And we'll come back to their more general approach, but for now I'm just going to say how you would use what Shear and Storch talk about to do computations for the local degree. So if P is K rational, then this max ideal corresponding to P, MP, is generated by linear forms. And more generally, we can write each Fi as a sum over some multiple, some polynomial multiple of the xj minus pj's. So really what we're seeing here is just if I plug in P, F should vanish. That means it's living in the ideal generated by these guys. And so I should be able to write this down for some Eij living in say my local ring. Well, I guess really we want to be working say just in the polynomial ring. Okay, and then we define capital E to be the determinant of these Eij's mod out by F, by the F1 through Fn. And Shear and Storch give us a linear form, it's a K-linear form, which they call eta. And it goes from this local algebra down to K. And it satisfies eta of this element E equals 1. Okay, so this is kind of the first thing that they do for us. And the next step is a result of Eisenbud-Levine and independently Kimchiashvili. They say, take any linear form, so it doesn't have to be eta, but take any linear form satisfying lambda of E equals 1. We can write down a bilinear form for this linear form. So we're going to call it the EKL form. And it just sends x comma y to lambda of xy. So since we're working in a commutative ring, this is a symmetric bilinear form. Eisenbud-Levine and Kimchiashvili show that this is a non-degenerate bilinear form in the situation that we care about. And Kirsten and Jesse actually show that the local degree is given by this bilinear form. This was inspired by So the real result of Eisenbud, Levine, and Kimchiashvili is over the real numbers, this bilinear form computes the topological degree by taking its signature. And then Jesse and Kirsten put in a lot of work to generalize this, and it gives us a nice equality, a nice way of computing the local degree at rational points, for example. With a little more work, you can make this work over more general points. You have to worry about how you like maybe base change and that sort of thing. But at the very least, it gives us a formula for computing the local degree. So a quick example of this. Let's take f to be y minus x squared comma y at the origin. Chasing this through, so y minus x squared is minus x times x plus 1 times y. Y is 0 times x plus 1 times y. And so well, I compute the determinant of minus x, 0, 1, 1. This is minus x. And so I'm going to define my bilinear or my linear form. I just need to define it on basis elements, since this is a k linear form on a k vector space. And the quotient by this is generated by 1 and x, since I've killed off y and I kill off x squared. And so I'm just going to define lambda of 1 to be 0 and lambda of x to be minus 1, so that lambda of minus x is 1. And the bilinear form you get, well, if I pair off these guys, I should get a minus 1 for the x's. I get 0 on 1, and then x squared was killed in my ring, and so that's also 0. And this is just the bilinear form, 1 plus minus 1. So up until now, this is how we've done computations for local degrees. And if you want to compute a messy global degree, you try and reduce to a simple local degree computation, and then use this approach, use this formula. Okay. So now we can start talking about what to do in general. So the more general approach. And it's going to combine some of the ideas of Kazanov, some of the ideas of Kirsten and Jesse, as well as kind of some more classical theory coming from commutative algebra on residue duality stuff from complete intersections. And then also a recent paper of Kirsten Wickelgren and Tom Bachmann, where they show in general that the EKL, or that the Shear-Storch form, this thing that Shear and Storch compute, really does compute the local degree in a great generality. So more general approach. As I've said, this is joint with Thomas and Sabrina. And some key ingredients. We're going to use work of Shear-Storch. We'll use a paper of Becker, Cardinal, Roy, Jafraniak. And Bachmann, Wickelgren. Okay. So the starting idea is that when Shear and Storch constructed this eta, we talked about it for local complete intersections, but they actually do it for global complete intersections as well. They do it in a pretty broad generality. And so if we can find a way to relate local Shear-Storch forms to global Shear-Storch forms, then maybe we can actually compute a global degree in terms of the global Shear-Storch form. So they give eta from the quotient. So now I'm just taking the polynomial ring mod out by the ideal generated by the morphisms. not localizing. And they also give the local picture that we've been talking about. And this local picture, their construction really doesn't depend on having rational points. Earlier, we stated it in terms of rational points in a way that was necessary for the Eisenbud-Levine-Kimchiashvili approach. But in general, if you just care about this eta rather than a more general linear form, you don't need to worry about P being a rational point. It can be any sort of closed point, as long as your morphism has an isolated zero at that point. Okay. So then what Tom and Kirsten do is they say that the local degree is given by the bilinear form coming from the local Shear form at any isolated zero. Okay. And so then what Thomas and Sabrina and I do is we give algebraic formulas, and I'll talk about them in just a second so that we can get to the fun stuff. We give algebraic formulas for the global Shear form and the local Shear form. And then we build on the work of Becker, Cardinal, Roy, and Jafraniak. So to describe a local to global principle for these bilinear forms. And really what the local to global principle does is it just tells you that the global Shear bilinear form coming from eta is a direct sum over all the max ideals of Q of these local guys. Okay. So using these two new pieces of information, we can say that the global degree is given by eta. It's given by this global Shear form. And the proof is, well, the global degree is a sum of local degrees by Kass-Wickelgren. And this is a sum of local Shear forms by Bachmann-Wickelgren. And this is this is just the global Shear form by the local to global principle that we talk about. So I'm going to focus on writing down a procedure for calculating these two bilinear forms. And then if we have time, I can get into some of the details about maybe how do you actually prove that formula. We could also talk about the local to global principle if we have lots and lots of time. Okay, so the formula for these two bilinear forms. So I'm going to start with F1 through Fn. These give me endomorphisms of affine space. And I want isolated zeros. Okay, so as long as these polynomials define a complete intersection, this machinery works. So you could think of just saying that the quote that Q is a complete intersection. Okay, and we're going to define a generalization of the Bézoutian that Kazanov talked about. We're going to talk about a multivariate Bézoutian. So we start with something we call delta ij. And this construction is not new to us. This is a classical tool from residue theory and commutative algebra. And the formula is going to look a little crazy at first, but it's really essentially just a partial derivative. That's what you're trying to do here, is you're approximating a partial derivative of your FIs. Okay, so I'm going to have two sets of variables, x's and y's. And I'm going to start by listing j minus 1 y inputs. And then the remaining inputs are x's. And then I'm going to minus off, I'm going to start with jy inputs. And then the remaining inputs are x's. And then I'm going to divide all of that by xj minus yj. So this looks like the Bézoutian that we saw in Kazanov's approach, but this is just for specific I and j. And then we're going to define the Bézoutian of f to be the determinant of these delta ij's mod f of x and f of y. So by this, I mean mod out by f1 with all x variables, f2 with all x variables, and do the same for the f1 with all y variables, f2 with all y variables, and so on. Okay, so then the next step is pick a basis. Let's call it AI of, if you're working in the global case, you pick a basis for your polynomial ring mod out by your ideal, Q. And if you're working in the local case, you just pick a basis of the local ring, the local algebra. Okay. So the procedure is the same once you've picked your basis. You write your Bézoutian as a sum over I and j. You have some coefficients. And you just write it in terms of the basis on the x variables and y variables. And then the matrix Bij computes the global degree in the global case or the local degree in the local case. So this is the global degree if you're working globally, and this is the local degree if you're working locally. Okay, so there was a lot of symbols and stuff written down. I'm going to do an example to kind of help this make sense, and then we'll see that this really does compute global degrees and local degrees. So I'll start with a fairly simple example. I'm going to take f to be x1, x2, x1 plus x2. And so I need to compute delta 1, 1. And this is x1, x2 minus y1, x2 over x1 minus y1. This gives me x2, 1, 2. This is y1, x2, y1, y2, x2 minus y2. So that gives me a y1. And then I will skip ahead here. These will both give you 1. And so then we want to compute the determinant of x2, y1, 1, 1, which gives you x2 minus y1. But we're not quite done yet because we need to choose a basis of our local or global algebra. So in this case, we're looking at Q is k adjoin x1 comma x2 mod out by x1, x2, x1 plus x2. So a nice basis for this would be 1 and x2, for example, because this relation here kills off the x1s in that basis. So I'm going to pick my basis to be 1 comma x2. And then this tells me that negative x1 is x2, negative y1 is y2, where I've just swapped out my x's for y's in this basis. And so with respect to this basis, the Bézoutian is presented as x2 plus y2. And so you can compute it just by writing down your basis elements and then looking at the coefficients showing up for each of these products. So there's no constant term. I'm going to get a 1 and a 1 for these x2 and y2 terms. And then there's no x2, y2. And so that will be a 0. And this computes the global degree as a hyperbolic form in this case. Okay. Now, if I wanted to do this computation locally, all that changes is the basis. The only step that you change is when you're computing your basis and then presenting your Bézoutian with respect to that basis, and then you proceed the same way afterward. Okay. So this gives a fairly algorithmic way of computing global degrees, local degrees in a nice general setting, and kind of, at least in my perspective, ties together some of the ideas of Cazanave and Kass and Wickelgren, and uses some nice work of Bachmann-Wickelgren to kind of package this all together, building on the foundation that Shear laid with their duality theory for complete intersections. Okay, are there questions at this point? Anything that I can help explain?
So the hyperbolic form is sort of seems to be appearing in almost all the examples. Is that
Yeah.
Are there some examples where we get a different answer, or is it,
Yeah, it's a good question. So Quick, Strawn, and Wilson have a recent paper on local degrees and the sorts of bilinear forms that can show up as local degrees. And they have this lemma in there where if you have a rank 2 local form, then you always get H as a summand. So if you wanted a more exciting situation, I can pull up an example and work it through of a local computation that is not a hyperbolic form. It's a rank 2 non-hyperbolic form, but it really uses the fact that we're working at a non-rational point. So it's kind of a weird example. Let me pull that up and do that. I think that's fun. I have to make sure I don't confuse myself as I'm doing it. Okay, so let's try let's see. Didn't write this one out beforehand. So this is a risky move, but let's see if I can do it. Okay, so this is going to be our morphism. And I'm going to assume A, B are in K, they're not 0. And A over B, not a square in K. So the point of this is I'm going to compute a local degree at the non-rational point that comes from this piece of the morphism. So if I plug in like a square root of A over B, then I should be able to get a nice root, but it's not a rational root. And so the techniques of like the EKL form, the Eisenbud-Kimchiashvili-Levine form, break down. And so this is something that we can do. So let's compute let me see what I have written down. Maybe maybe I'm going to embarrass myself if I try and do this live. I'll just say that you can compute the local degree of f at, let's see, this should be, if I pick 1, comma, the square root of a over b of f. When you do this, you should get bracket ab. Okay, so I'll save the computation, but you can go through the process. I was just looking at my notes and realized that I would. You never want to show too much when you're live. So.
Thanks a lot for it's homework for the rest of us, I guess.
Yeah, it's fun practice. So, yeah, but I'll say, so when we first did this example, I was worried that there was a contradiction somewhere, but this does not contradict the result of Quickstrawn and Wilson about having an H summand for a local degree, because that's relying on the fact that you're computing EKL forms at rational points. This is not a rational point, and so you don't have to worry about that. Okay. Great. So I've just got a couple more minutes. Let me spend a little bit of time talking about how we, maybe I'll show why the Bézoutian relates to this Shear form, because I think that's kind of one of the places where, at least for me, it was exciting to see this connection. So how does this Bézoutian relate to Shear eta? Okay, so we'll start by talking a little bit about how eta is actually defined. So eta is defined in terms of a particular determinant. Delta. If you've read their paper, you've seen this delta and have maybe wondered how to actually compute it. And we won't have time to really get into the details of how they use delta to compute eta. But the key idea behind delta is I'm going to take the multiplication map from my polynomial ring tensor itself down to the polynomial ring. And you're just sending A tensor B to AB. Okay, and so the kernel of this map is generated by your variable tensor 1 minus 1 tensor your variable for all your variables. That's how that you can generate the kernel in this form, because everything is built up out of these pieces. And the fact that fi tensor 1 minus 1 tensor fi is in the kernel of f means that you can write this as a sum over j of these kernel generators. Okay. And so what Shear and Storff prove is the image of the determinant in the quotient. So let's just say in Q tensor Q, this does not depend on your choices of the aij's. So there are all sorts of ways that you could write down this sum. There's not a unique way to do it. But once you pass to this quotient, whatever choices you made didn't matter when you're computing this determinant. So this does not depend on your choices of aij. Okay, and so what we're going to do is show that these delta ij's, in a sense, satisfy the properties they need to be a good substitute for aij. So delta ij works as a choice for aij. And the idea behind this is if you write out, so take the sum of these delta ij's times xj minus yj. This ends up being a telescoping sum. If you remember, this was like an fi with some inputs minus an fi with some different inputs divided by xj minus yj. And so the xj's and yj's cancel out. And you have what ends up being a telescoping sum. These first and last pieces cancel out until you're just left with fi with just x variables minus fi with just y variables. And so using the isomorphism between the tensor and the polynomial ring in two variables, you can really go between these by sending a tensor b to a of x, b of y, and you send these xi's to xi tensor 1 and the yi's to 1 tensor xi. Using this dictionary, you can show that the image of the delta ij's really do behave like the aij's. And so this is one of the kind of key insights that allows us to relate this commutative algebraic formula through Shear to the work of Bachmann-Wickelgren, for example, on computing the local degree in terms of the Shear form. Okay, so I think in order to not run past 5 o'clock Norway time, I will end there. But I'm happy to expand on anything if people have questions.
Okay, thanks a lot for a nice talk. Let's unmute and thank the speaker. Okay, great. So we can open for some questions. Please go ahead.
So Kazanov also has these formulas for adding functions from P1 to P1. And you know, there's some sort of Bézoutian condition on a denominator with some explicit matrices. Have you thought about multivariate addition by suspension? You know, an explicit formula in terms of algebra.
We haven't quite gone there yet. We've kind of done the check on the ring structure. So if you take F composed G, then the degree of that should be the degree of F times the degree of G. So the ring structure on this class of maps. But we haven't yet gone into, I think the addition structure is a little bit harder. But that's a good question. We should definitely, I'm gonna actually make a note to myself to thank you.
As a selfish question, this looks like a computer. Having this one-stop formula for the whole degree looks like you could put in equations to a computer and get out the degree. So I was wondering if you were going to make that happen. The three of you would make that available, so the rest of us just plug in.
Yeah, I think that's something that we've definitely talked about and would like to do. I'm not necessarily the individual with I don't have great computer skills, but maybe we three can do it. Or if someone here is really excited about doing that sort of thing, I think we would be happy to have some help writing down a nice package. But I agree, it would be nice to have these tools just like so you can type it in and not have to write down the basis yourself. Thank you, Christian.
Yeah, great. Are there any other questions?
I guess I have a question. So if you were to just look at a map from P1 to P1, and I mean, there are these ways of expressing the degree as a sum of local degrees, but you're missing some information of the actual homotopy class, right? There's some extra unit you have to remember. Is there some way of figuring that out in terms of like the local degrees or something? Is there any good way to do that?
I would have to think about that. I mean, so like if you restrict the formula for delta ij in the univariate case is then just the Bézoutian that Kazanov writes down. But I don't think anything that since we're working in like higher dimensions, I would be surprised if our proofs would see this extra, like the k star factor of the degree,
Right.
Because you don't have that in higher dimensions, and there's no dimensional assumptions on what's going on here.
Okay.
So, but yeah.
Okay, thanks.
Thank you.
Okay, maybe a last question. Go ahead. Oh, I think we're all very happy. So thanks again, Steve, for a wonderful talk.